Let's elucidate quantum cryptanalysis. In this video, we will investigate quantum search and quantum counting. In the quantum search algorithm, we will use the unitary operator denoted by U sub theta. We can think of this unitary operator as a rotation by the angle theta. We can also think of this unitary operator as a composition of two reflections. Consider the following combination. We have minus the identity operator plus 2 times the projector that is formed from this state, which is labeled by 0. We're going to put a beta as a superscript over here, and that's to remind us that we're dealing with a beta qubit register. So we have a register of qubits, and if we count all those qubits, the total that we get is beta. So what does this state actually mean? When we put the label 0 over here, that means we can also think of this as a string of beta zeros. And that's telling us that we need to initialize all of the beta qubits in this register in the computational basis state that is labeled by 0. So we're taking that state and we're putting it in this ket-bra combination. And this ket-bra combination is a projector. I'm going to take that projector, multiply it by 2, and we're adding that to minus the identity operator. And note that we're specifying the dimension of the Hilbert space in the subscript. So 2 to the beta is the dimension of the Hilbert space for a beta qubit register. So now let's take this combination and sandwich it in between multi-qubit Hadamard gates. So we're going to have capital H, which denotes the Hadamard gate, and then in the superscript we'll put a tensor product beta. So that means that we're applying Hadamard gates to all beta qubits in this register. And we're going to do a sandwich. We're going to do that on both sides over here. And this is one of those two reflections. But we also have another reflection, which we can call the oracle. And the oracle has the following format. We can write it as the identity operator minus 2 times, and we're going to have some projectors, but it's not just going to be this projector over here. It's going to be a sum of all of the target projectors. So we can write this as the sum over all of the little t's, which are elements of the set big T. The set big T contains all of the targets of search, and these little t's are those targets. And we're going to use the little t's as labels for these ket-bra combinations. And we'll put a beta in the superscript to remind us that these states that we're using to construct the ket-bra combinations, they are beta qubit states. So we can represent these little t's as strings of beta bits. And those strings of beta bits can be used as labels for these beta qubit computational basis states. And we're putting them in these ket-bra combinations, and that gives us projectors. So we have this coefficient of 2 over here. That's because when we have this identity operator and we subtract 2 times these projectors, that's going to have the effect of flipping the signs of those projectors. So the identity operator can be written as a sum of all of the projectors that have this format. So we consider all of the beta qubit computational basis states, and we can put them in these ket-bra combinations, and we take the sum over all of those states. And so in this identity operator, we have all of the non-target projectors and all of the target projectors. And what we're doing by subtracting this combination is flipping the sign on those target projectors. That means when this oracle acts on a beta qubit computational basis state, it's going to mark the target states with a minus sign. And it's not going to do anything to the non-target states. So it's just going to be like the identity operator acting on a non-target state, but when it sees a target state, it's going to put a minus sign out the front. That's a phase factor of -1. So that's what we're using to distinguish the targets from the non-targets. So the oracle can be thought of as a reflection, and then we have this other reflection over here, and that gives us a composition of 2 reflections, which we can treat as a rotation by the angle theta. Now we need to consider a very important condition. The total number of targets, which we can write as the cardinality of the set big T, this needs to be less than 2 to the power of beta minus 1. So 2 to the power of beta, that is the dimension of the Hilbert space, and 2 to the power of beta minus 1, that is 1/2 of the dimension of the Hilbert space. So we need this inequality to be satisfied. And this is actually how we choose the value of beta. This is how we choose how many qubits we need in our register. So if this is not satisfied, then we have to add more qubits to the register. We have to make beta larger so that this inequality is satisfied. So now let's have a look at what the quantum search algorithm does. So the goal of the quantum search algorithm is to take this unitary operator, u theta, and iteratively apply it q times to the state that is labeled by plus. And again, we have this superscript beta. So this plus state is shorthand notation for a uniform superposition of all of the beta qubit computational basis states. So that includes all of the target states and all of the non-target states. They're all present in this uniform superposition. In total, we have 2 to the power of beta qubit computational basis states. And only some of them are target states. So now let's see what happens if we iteratively apply u theta q times to this state. That's going to give us cosine of theta times 1/2 plus q as the coefficient for the non-target superposition. And then we're going to have another term, so plus sine of theta times 1/2 plus q, and that's the coefficient of the target superposition. The non-target superposition is a uniform superposition of all of the non-target beta qubit computational basis states. The target superposition is a uniform superposition of all of the target beta qubit computational basis states. And what we want is to choose q such that this coefficient is very large and this coefficient is very small. We want to choose q so that we can do amplitude amplification. So we want this to be close to 1 and this to be very close to 0. That means we can make the approximation that this is just equal to the target superposition. And we can write the target superposition as 1 over the square root of this cardinality of the target set. So the number of targets over here, that's in the normalization coefficient. And we want to times this by the sum over all of those little t's that are elements of this set big T. And these little t's serve as labels for beta qubit computational basis states, and all of these are considered to be target states. So our goal is to measure these target states. And we can measure these target states by preparing some state which is approximately equal to the target superposition. That means that the amplitude associated with these target states is very large compared to the amplitude associated with the non-target states. So this can be thought of as amplitude amplification. So that's what we're doing in the quantum search algorithm. Now let's define this angle theta in terms of the number of targets. So if we consider the ratio of the number of targets divided by 2 to the beta. So 2 to the beta is the dimension of the Hilbert space of this beta qubit register. This is equal to sine squared of pi times theta on 2 pi. And equivalently, we can write this as sine squared of pi times 1 minus theta on 2 pi. So if you cancel these pi's over here, you're going to get sine squared of 1/2 of theta. And then if you take the square root of both sides of this equation, you can see that sine of 1/2 of theta is equal to the square root of this ratio. So if we consider the special case where q is equal to 0, that means we don't apply u theta at all, this q will disappear from the argument of these trigonometric functions, and we'll be just left with 1/2 of theta as the argument. So in that special case, we can have a look at this definition. So the angle theta is defined in terms of this ratio. So why do we need to know this ratio? Well, it's because it's going to help us determine Q. And we want to choose Q so that this approximation is valid. So let's see a format for Q that's going to allow us to make this approximation and successfully implement amplitude amplification. So we need Q to be equal to pi over 2 theta. And because Q is an integer, we're going to take the floor of this value. So this value will guarantee that this approximation is a valid approximation, and we have a very large amplitude for these target states and a very small amplitude for the non-target states. Now, we can write theta in terms of the number of targets. So that means this bottom part of the fraction is going to turn into 4 times the inverse sign of the square root of the number of targets times 2 to the minus beta. And this is all in the square root. And the top of the fraction is still pi. And we have to take the floor of this to give us an integer. So where did this come from? Well, if you cancel these pi's, take the square root of both sides, then apply the inverse sign to both sides, and double both sides, that's going to allow you to isolate theta. So you have an expression in terms of this total number of targets, and that's going to allow you to have an expression in terms of theta. And you can substitute that over here, and because of this theta on 2, we have to move that 2 to the other side, and that's why this 2 becomes a 4 over here. So we can write Q in terms of the number of targets, or we can write it in terms of theta. So to perform the quantum search algorithm, we need to know theta. And knowledge of theta is the same as knowing how many targets there are. So we can put an upper bound on this. We can write this as, this upper bound is pi over 4 times the square root of 2 to the beta, that's the dimension of the Hilbert space, divided by the number of targets. And if we want to make this an integer, we can take the ceiling function over here. So this is the ceiling function, and this is the floor function. So we have an expression for Q, and we also have an upper bound for Q, which is written in terms of the square root of the dimension of the Hilbert space. And over here we have this number of targets that is dividing the dimension of the Hilbert space. So that's the reciprocal of this ratio that we have. Now that brings us to the quantum counting algorithm. So if we want to do quantum search, we have to know how many targets there are. And if we want to know how many targets there are, we have to do the quantum counting algorithm. Now the quantum counting algorithm shares a lot of similarities with the quantum order finding algorithm. So we're going to use a control register, which contains alpha qubits, and a target register, which contains beta qubits. We need to prepare the following state. We need to prepare the control register in the state that has 2 to the minus alpha on 2 as a normalization coefficient. And then we have the sum over the index zeta ranging over the integers mod 2 to the alpha. And we're going to use this z as a label for the alpha qubit computational basis states that are present in this uniform superposition. And then we're going to need the state u theta applied z times to the plus state. So this is our beta qubit register. That's the target register. This is the control register, and this is the target register. Now note that we have the same expression over here, except we're changing q to z. And this z is the same as the label that's present in this uniform superposition. Once we prepare this quantum state, we need to apply the inverse quantum Fourier transform to the control register. And now that we're at this stage over here, so this is the quantum state that we need to prepare for the quantum counting algorithm, we also need to talk about the eigenstates of this unitary operator. So the eigenstates can be written as this notation over here. So we have plus or minus I as the label for these states, and we can write them as the non-target superposition plus or minus I times the target superposition. And we can divide that by the square root of 2. That's a normalization coefficient. So when this unitary operator, u theta, acts on one of these eigenstates that are labeled by plus or minus I, it has the effect of multiplying by e to the minus plus I theta. So you can see the sign is opposite over here. So this is an eigenvalue equation. So we have the eigenstate over here, and then we have the eigenvalue present over here. So we're going to use this relationship now when we do some expansion. So this quantum state that we need to prepare in the quantum counting algorithm can be rewritten as 2 to the minus alpha on 2 times the sum over z ranging over the integers mod 2 to the alpha. And then we can expand this inverse quantum Fourier transform acting on the alpha qubit computational basis states. That will give us 2 to the minus alpha on 2 times the sum over another index, which we can call x, ranging over the integers mod 2 to the alpha. And then we have e to the minus 2 pi I zx 2 to the minus alpha, and we change the label from z to x. So we saw this in the quantum order finding algorithm as well. And what about this state? Well, we can write this state as 2 to the minus 1/2 times the sum over the index zeta, which takes on two values, plus 1 and minus 1. And then we're going to have these coefficients of the form e to the zeta I theta times z plus 1/2. So you can see that theta times z plus 1/2, that argument looks very similar to the argument that we had over here for these trigonometric functions. Now that's not a coincidence. These coefficients are multiplying the states labeled by minus zeta I. And if you take this definition for the plus or minus I states, you can substitute that definition in over here. And then you can do some algebraic manipulation, and you can identify that the trigonometric functions, sine and cosine, can be written in terms of these complex exponentials. So this will give you the same format of this equation. The only difference is that you will have a z in place of q. So just replace this q with z, and this equation over here is equivalent to this expression. So you can verify that by substituting this definition of the eigenstates and expanding those terms out, and then using the definition of the trigonometric functions in terms of complex exponentials. So now we've expanded this inverse quantum Fourier transform term, and we've also expanded this in terms of the eigenstates. Now let's do some rearranging, and that's going to give us the following expression. We're going to have 2 to the minus 1/2 times the sum over this index zeta, which takes on two values, plus 1 and minus 1. And then we're going to have the sum over x, which ranges over the integers mod 2 to the alpha. And now we can consider a coefficient. So we can group these two normalization coefficients into 2 to the minus alpha, and then we'll have the sum over zeta ranging over the integers mod 2 to the alpha, and we can start to group these exponential terms together. We can write this as e to the 2 pi I times zeta theta divided by 2 pi, and then we can subtract off x, but we're going to shift x by the alpha bit approximation of zeta times theta over 2 pi. And we need to multiply this by 2 to the minus alpha. And then we'll close the bracket over here, raise this to the power of z. Now let's have a look at this combination. If we bring this z back in and we undo this shift, we can recover this minus zx 2 to the minus alpha term. So if we undo that shift to the variable x. And if we bring this z over here and we cancel these 2 pi's, we can recover this term where we have zeta times theta times z. So here we have zeta and theta, and we can just bring that z in. But we mustn't forget that we also have this 1/2 term. So we can write that as e to the zeta I theta on 2. So that is another term that we also need to include in this coefficient. So this coefficient is a little bit different from the coefficient that we saw in the quantum order finding algorithm, because there's this extra phase factor present over here. Now let's have a look at what's happening to the quantum states. Well, we can write these quantum states as x plus, we have to shift this, the alpha bit approximation of zeta theta on 2 pi. And when we write this inside the label over here, we're doing addition mod 2 to the alpha. So we're doing modular arithmetic. And then finally, we're going to have minus zeta I. And we'll put a beta over here. And this beta is telling us that that is this beta qubit target register state. And that's the eigenstate over here. And we have two values given by the two values of zeta over here. We have +1 and -1. Now let's do an approximation. So just like we saw in the quantum order finding algorithm, if we choose alpha to be sufficiently large, then we can make the approximation that there is going to be a peak in the amplitude associated with x equals 0. And that means that this term over here, which we can identify as the sum of terms in a geometric series, this is going to only give us a significant value corresponding to x equals 0. And that means we can produce the following approximation. So this is approximately equal to 2 to the minus alpha. I'm going to write out the two terms. So the two possible combinations for zeta equals +1 and zeta equals -1. So what is that going to give us? First, we're going to have e to the plus I theta on 2. Then we're going to have the alpha bit approximation of theta on 2 pi as the label for this alpha qubit state. So that's zeta equals +1. And over here, we're going to have minus I as the label for this eigenstate. So that is +1 times -1, which gives us -I. And the other state is going to have the following format. We're going to have e to the -I theta on 2. So that corresponds to zeta equals -1. And then we can write this as the alpha bit approximation of 1 minus theta on 2 pi. That's because we're doing modular arithmetic, mod 2 to the alpha. And then finally, we're going to have the state labeled by +I. That's because we have minus times -1, which gives us a plus. And we'll close the bracket over here. So if we choose alpha, such that it is sufficiently large, then we can make that approximation that we get a peak in the amplitude corresponding to x equals 0. And then we will just get these two terms. So this is the normalization coefficient. And if we measure the control register, we measure this alpha qubit control register, then we're going to have these two possible values. So if you consider this alpha qubit approximation of theta on 2 pi, that is approximately equal to 2 to the alpha times theta on 2 pi. And if you consider this value, so that corresponds to the minus value. So we have the alpha bit approximation of minus theta on 2 pi. That is equal to the alpha bit approximation of 1 minus theta on 2 pi, because we're doing modular arithmetic, mod 2 to the alpha. And this is approximately equal to 2 to the alpha times 1 minus theta on 2 pi. So that allows us to construct an expression for the number of targets. So we can either substitute this approximation for theta on 2 pi, or we can substitute this approximation for 1 minus theta on 2 pi. And both of those possible values that we can measure here are going to give us an approximation for this ratio. So that means that the total number of targets, which we can count using the quantum counting algorithm, is going to be approximately equal to 2 to the beta times sine squared, and we have pi 2 to the minus alpha. We have to rescale because of this 2 to the alpha factor. And then we're going to have the alpha bit approximation of plus or minus theta on 2 pi. And we can close the bracket over here. So this is an approximate expression. So we have this 2 to the beta. That's the dimension of the Hilbert space for this beta qubit register that we're dealing with in quantum search. And then we have 2 to the minus alpha. Alpha is the number of qubits that we have in this control register. And we want to measure the control register. And we're going to have a really high probability of measuring the alpha bit approximation of this ratio, theta on 2 pi, or we're going to have 1 minus theta on 2 pi. So these are alpha bit approximations. And this approximation is only valid if we have a sufficient choice for alpha, which gives us a peak in the amplitude associated with x equals 0. So to do quantum search, we need to count the number of targets. And we can count the number of targets by preparing this quantum state and then measuring the control register. And that's going to give us a high probability of measuring these two outcomes. And either one of those outcomes can be substituted into this expression over here, and that can give us an approximate value for the number of targets, and that allows us to find Q. And Q will allow us to do amplitude amplification and prepare this target superposition. And then if we measure that target superposition, we can measure one of these target beta qubit computational basis states. And if we repeatedly do that, we can get all of the targets that are encoded by this oracle.